everyone, and welcome to the lecture. Congratulations on completing the Igneous Petrology part of the module, and now it's time to dive into the world of metamorphics. So my name is Dr. Soraya, and I will be teaching you about the introduction to metamorphism and the classification of metamorphic rocks. Alright, so before we get on the road and get into metamorphism, let's consult our roadmap really quick. So for this week, we're going to start things off by talking about the introduction to metamorphism, what kind of things drive metamorphism, what are the agents that drive metamorphism, why we should study metamorphism in the first place, and then next we're going to talk about where this happens, so in terms of plate tectonics, where does metamorphism happen, what happens at subduction zones, what happens when it's surrounding a magma body, and then once we talk about where this happens, we want to know what kinds of metamorphism there is out there. So we're going to touch the types of metamorphism, which relates to the processes and also the settings, and then next, once we've done these three, we're going to move on to examples of metamorphism. So here we're going to talk about 5 case studies. Sounds like a lot, but don't worry, we'll go through it one by one, and you will see why it is important to study metamorphism in the first place. And last but not least is the part that I personally like, because you get to look at lots of rocks, is the classification of metamorphic rocks. So here we will be talking about how we classify rocks into the different categories and how you name them and why you would name them those names. So at the end of the notes, as I mentioned, you will find references to the books that I've used to prepare these lectures, and hope it will help you on your metamorphic journey as well. Okay everyone, so one last slide before we begin our lectures officially. I would just like to remind everyone to be prepared before each lecture. So that means make sure you have your favorite notebook, your favorite pen, your device charger nearby, and if you're the type to annotate on notes, make sure your notes are printed out beforehand. That will make things easier and quicker as the lectures go on. And also remember to take care of yourself. So compared to physical lectures, you're allowed to have snacks in this class. Have as many snacks or as little snacks as you want. Don't forget to stay hydrated. Take regular breaks. You don't have to watch all 5 lectures in a row. Hit the pause button, step away from the screen, and relax for a little bit. It's okay. And if you are visiting the library or you need to be on campus, I don't know how things will be once this lecture is released, but always remember to take care of your personal hygiene, wash your hands regularly, carry some hand sanitizer with you, and also don't forget to wear face covering to protect others. And yeah, and don't forget to keep your physical distance, and hopefully we'll be able to be in class together physically one day soon. Okay, on to our lectures then. Okay, so welcome once again to the first lecture in this series. So we are going to have an introduction to metamorphism. Before we dive into the specifics, let's first get to know what metamorphism means. So metamorphism comes from the Greek meta, which is a prefix that denotes something happening after, and morph, which is form or structure. So basically what this means is metamorphism refers to a change in form. The emphasis here is on change. And in geology, we have this definition proposed by the IUGS SCMR. It is pretty long, but it's covering all of the bases, and we'll break that down one by one. So first of all, metamorphism is a subsolidus process, which means that if you look at a phase diagram, it is a part that lies below the solidus, so it represents a system that is wholly solid. Leading to changes in mineralogy and or texture. So we have changes in mineralogy and or textures. And we also have change in chemical composition in a rock. So we have three things now. So we have that it's a process that happens in a system that's wholly solid. And we have two changes mentioned already. So we have change in mineralogy and texture and change in the chemical composition. Next in the definition, we have these changes are due to, so now we're knowing why it happens. So it happens due to physical or chemical conditions that are different. So differ. So they're different from those normally occurring at the surface or below the surface, and they may coexist with partial melting. So again, with emphasis on change, it can be due to the chemical conditions where it differs from those normally occurring at the surface or in zones of cementation and diagenesis below the surface. So all of this will make more sense when we look at the phase diagram in the future slides. But just to recap this once again, the definition proposed by the IUGS basically says that it is a process happening in the subsolidus. It involves change in mineralogy and textures and in chemical composition, and this is due to physical or chemical conditions that differ from those normally occurring. So it's something different. So it's something different in the environment that causes change in a system that is wholly solid. So remember, metamorphism, the key word here is change. Okay, so one last time, just to drive the point home, metamorphism is the changes that occur in the solid state to a rock's mineralogy and texture as a result of the input of thermal energy and or mechanical energy. So we talked about change in mineralogy and texture. And what does that mean? So we have here textural changes and mineralogical changes. So textural changes, we are talking about the grain size and shape. So grain sizes and shapes may be altered, and some grains may develop a preferred orientation. So when we talk about textural changes, it's the size and shape of grains and their preferred orientation. That's the kind of change that it has. Next, when we're talking about mineralogical changes, we're referring to recrystallization, so having existing minerals adopt new textures, and neomineralization. So neo, which means new, means that there is a formation of new minerals at the expense of existing ones. So this is the result of chemical reactions. So those are the two changes that we will be paying attention to in the process of metamorphism. So some of you might think like, it's already solid, how can a solid thing change? So actually, if we look at this diagram here, no crystal is perfect. So there are holes, vacancies in the crystal lattice, and these give atoms spaces in which they can move around. So if we pay attention to these darker ones here, you can see that these atoms can migrate and rearrange without actually destroying the integrity of the solid. So this solid is still a solid, but these atoms can move around thanks to these vacancies. So the dark atoms, which were previously further away, are now closer together than they were earlier. And that's how change happens within a solid. So this example here is an example of mudstone going and turning into slate. Before we move further, let's have a quick pit stop and revise on some basic concepts. So let's have a look at the definition of the following things. What is petrology? What is a rock? And what is a mineral? Okay, so petrology is the study of rocks. And in geology, it is the branch of geology concerned with the origin, structure, and composition of rocks. So these are the three things that we will be focusing when we talk about metamorphic petrology. And so what are rocks? Rocks are naturally occurring assemblage of minerals. And what are minerals? Minerals are naturally occurring homogeneous solid, inorganically formed with a definite chemical composition and an ordered atomic arrangement. Okay, so now that we've got that down pat, we can move on to the next section. Okay, so before we move even further, let's talk about the rock cycle for a moment. So you've probably come across the rock cycle before in some point of your degree, and if you're looking at it now, you'll realize that the different types of rocks and their processes are closely interconnected. So the question is, what are the limits to metamorphism? Where does metamorphism start and end? When does it start being an igneous process where melting happens? Or when does metamorphism start? Because the burial of sediments makes sedimentary rocks. And when does it stop being a sedimentary rock? And when does it start being a metamorphic rock? So these are the sort of questions that we'll attempt to answer in the next few slides with the limits of metamorphism. So to separate metamorphism from the processes of sedimentation and the processes involved in igneous rocks, we will be having a look at the temperature and pressure limits of metamorphism. So we have the low temperature limit of metamorphism and the high temperature limit of metamorphism, followed by the low pressure limit of metamorphism and the high pressure limit of metamorphism. So those two things we will be focusing on, temperature and pressure. First of all, let's talk about the low temperature limit of metamorphism. So this low temperature limit, meaning the lowest temperature at which metamorphism can happen, would be set between 150 degrees Celsius to 200 degrees Celsius. And the temperatures where this sets in is strongly dependent on the material under investigation. So for example, with sedimentary rocks, so mineral transformations happen shortly after sedimentation and it proceeds continuously after increasing burial. So as you can imagine, this is increasing pressure but has quite little to do with temperature. So continuous burial of sediments helps it metamorphose in the long term. Another example would be the low temperature alteration of volcanic rocks, the precipitation of minerals in fractures, so that's another low temperature example, and also low temperature rock-water reactions which produce mineral-filled veins and fissures. So again, more minerals in fissures and fractures. So those are examples of the lower end limit of metamorphism. So if that was the lower limit of metamorphism in terms of temperature, what would be the higher temperature limit of metamorphism? So when does it stop being metamorphic and start being igneous? So high temperatures will cause rocks to melt. And when it melts, this becomes the subject of igneous petrology. So partial melting actually has both a metamorphic and igneous aspect. So if we have a look at this photo here, it's of a really interesting rock type called migmatite. So migmatite is a crustal rock that characteristically is produced by partial melting. So it's made up of residual metamorphic rock. So it has a metamorphic component and an igneous rock component due to the partial melting. So, in other words, the melting temperature of rocks defines the high temperature limit of metamorphism. So, melting temperature, this again is strongly dependent on the pressure, the rock composition, and the amount of water present. So, temperature for melting is dependent on three things: pressure, rock composition, and the amount of water present. So if water is absent, so no water, it will have a higher melting temperature. If it has water, then it will have a lower melting temperature. Okay, so here we have a graphical representation of those higher and lower limits of temperature in metamorphism. Don't worry about the pressure axes just yet, so let's just focus on this bottom here. So temperature. We talked about how the lower T limit for metamorphism would be about 150 degrees Celsius to 200 degrees Celsius. So looking at this graph right here, you can see that anything below 150 lies in the sedimentary diagenetic processes region. And we talked about how the higher temperature limit would lie in the region where rock melting happened. And this would depend on the rock. So if we look here on the bottom, we have two processes mentioned. So we have metamorphism and igneous processes. So we can see here that the upper limit of metamorphism actually falls somewhat inside the igneous processes region. And in this region we can see it corresponds to the formation of gneisses, which are high temperature, high pressure rocks. And we also have some gneisses here and eclogites here, which are metamorphic rocks as well. So depending on the type of rock, the high limit of metamorphism could be higher. So again, the higher temperature limit would depend on the rock melting temperature, which depends on the rock composition and also the presence of water. Okay, so we can see here that this particular curve, let me just change that color really quick. So this particular curve emphasizes that this is a water saturated melting of granite. So this one has lots of water, therefore a lower melting temperature. This one here is water absent, so no water, and you can see that it has a higher melting temperature. So hopefully that helps to illustrate the relationship between the upper limits, the presence of water, and the different types of processes involved. Another important player in the formation of metamorphic rocks is pressure. So we need to define the lower and upper limits of pressure in metamorphism. So the lower pressure limit could be found in the creation of contact aureoles. So we will talk a bit more about contact metamorphism later, but what you need to know now is that it is metamorphism that occurs around magmatic bodies, and it usually happens at a shallow depth, which means that it has low pressure because it's so close to the surface. Okay, so we've had a look at the examples for low pressure limit of metamorphism. So what about the other end? What about the high pressure limit of metamorphism? So there are two types of rocks that we can talk about, which are eclogites and gneisses, which form under high pressure. And we can look at a few examples of some specific eclogites and gneisses, which make them a great example of the higher pressure limit of metamorphism. So for example, if any of the rocks have coesite inclusions, this indicates that the pressure has to be at least 3 gigapascals. So that's pretty high. And we can see that eclogites, which are already a really high density, high pressure rock, have been found with garnets and even diamonds, which further indicates that it is a rock formed under really, really high pressures. And some of these rocks require at least 6 gigapascals to form. So because of these really high pressures, these rocks are very aptly named ultra high pressure rocks. So they undergo ultra high pressure metamorphism. So rocks formed at a depth of 100 to 200 kilometers below the Earth's surface, they have a corresponding pressure of more than 3 to 6 gigapascals. So as you can imagine, the further away you are from the Earth's surface, the higher the pressure would be. And this is where these high pressure rocks have formed. So just as a summary on the limits of metamorphism, we can divide this up into the following categories. So we have the first one we discussed earlier, the low temperature limit. So it's 0 degrees for processes in near surface environments. So we have stuff like rock-water interactions. If you remember the formation of minerals and fissures, or in fractures, and conventionally with metamorphism, we would put that between 150 to 200 degrees Celsius, because anything lower than that will fall into the sedimentary or diagenetic processes region. And next we looked at the upper temperature limit. So in crustal rocks, that would be about 750 to 850 degrees Celsius. The highest recorded one was about 1150 Celsius. And in regional scale metamorphics, the temperature doesn't exceed 700 degrees Celsius. So that is the upper limit of metamorphism. And as for pressure, as we looked earlier, it is about 0.1 megapascal, so really low compared to what we had just looked at. So 0.1 megapascals at contact to lava flows at the surface, so very low pressure. And as we discussed earlier, the higher P limit for some rocks collected at the Earth's surface, we now know that they've once formed at a depth of 100 to 200 kilometers, and that gives us a pressure of 3 to 6 gigapascals. So gigapascals, ultra high pressure. So yeah, that is the summary for what we just discussed, and we will be moving on to the next slide. Okay, so now that we've had a discussion about the limits at which metamorphism occurs, let's take a step back and talk about the origins of metamorphic rocks. So we're going to have a discussion about the protolith or the parent rock. So what are protoliths? So protoliths are Greek for proto, which denotes first, and lithos, which is rock. So basically what this means, it is the parent rock or the first rock that existed before metamorphism starts. So what type of rock would be considered as protoliths for metamorphic rocks? So if we're talking about rocks that existed before metamorphism, then we would be talking about sedimentary rocks and igneous rocks. So these two are the best candidates for protoliths. But some of you might be asking, what about metamorphic rocks? Can metamorphic rocks be parents to other metamorphic rocks? The answer is, basically, metamorphic rocks can undergo further metamorphism and they can be remetamorphosed. But, big emphasis on the but, it does not qualify as a parent rock. So, for example, if you had a mudstone, so mudstone is our sedimentary rock, and it metamorphoses into slate, and it continues to metamorphose into schist. In this case, you would say that the parent rock or the protolith for schist would be mudstone. You would not say that the protolith would be slate. So the critical feature of a parent rock is its mineral composition, because the stability of minerals count when metamorphism takes place. Any unstable minerals, and they will recrystallize into new minerals. So remember from our earlier definition, metamorphism is change that occurs due to a change in the original environment. So anything that's unstable, that will recrystallize into new minerals. As I mentioned earlier, the chemistry of the protolith is the most important clue towards deducing the parent rock. So as we move further down this journey into metamorphism, you can come back to the slide and have a look at the different types of rocks and what that means for your metamorphic rock. So just to list off a few examples, we have ultramafic rocks, mafic rocks, shales, we have carbonates, we have quartz rocks, and we have quartzo-feldspatic rocks. But again, this might not make much sense at this present moment, but you can always come back to the slide and see how that relates to the metamorphic rock that you're studying. Okay, so now we're going to move forward and talk about the controls over metamorphic processes. So we've touched briefly on two of the main key players, which are temperature and pressure. But we also have influence of deviatoric stress and fluids. Let us start with the first agent of metamorphism, which is temperature. So with temperature, we need to talk about the possible heat sources, and we have two possible heat sources, which are the radioactive decay deep within the Earth's interior and igneous intrusions. So with radioactive decay, this happens deep within the Earth's interior. And as you can imagine, the deeper down you go, the higher the temperature would be. And there's something called a geothermal gradient. So geothermal gradient basically is the change in temperature with depth. But we will talk about this more when we discuss plate tectonics and metamorphism. The next one, igneous intrusions. So this is a bit more of a local heat source. So it heats up what is closest to it. These two provide intense heat sources. And temperature has a pretty profound effect on metamorphism because it controls the stability of minerals. And the stability of minerals is a function of temperature, pressure, and the presence of fluids. And by fluids, we especially focus on water. So we'll have a look at these examples on the bottom to further elaborate this point. So first of all, let's have a look at clay minerals. So clay minerals aren't the most stable. They are stable up to a temperature of 150 degrees Celsius or 200 degrees Celsius. Anything above this, they transform into micas. Feldspars, on the other hand, are a bit more stable, where they are stable up to a temperature between 1000 degrees Celsius and 1200 degrees Celsius. And the most stable of these three, at least in this particular example, would be quartz. And quartz is stable from environmental temperatures all the way up to 1800 degrees Celsius. And if the pressure is higher, so if we remember, it's a function of temperature, pressure, and the presence of fluids. So if the pressure is higher, then the upper limit of this temperature would be higher. And if water is present, so with water, this would be lower, but without water, so if it was dry, the temperature would be higher. Some minerals will crystallize into different polymorphs. So what this means is that they are the same composition. So in this case, they're all Al2SiO5, but depending on the temperature and pressure, they will take on different crystalline structures. So in this case, we have three minerals, which are kyanite, sillimanite, and andalusite. We will go more in depth with PT diagrams, so PT graphs or PT diagrams, in a different video, because there is quite a bit to discuss about this. But what you need to know for now is that some minerals will crystallize into different polymorphs, and this is one of the most popular examples. So we have Al2SiO5, and you have three different minerals, which are kyanite, andalusite, and sillimanite. Next, we will be discussing the second agent of metamorphism, which is pressure. So pressure is important in metamorphic processes for two reasons. The first, mineral stability. If we recall from earlier, mineral stability is a function of temperature, pressure, and the presence of fluids. So this is where pressure plays a part. And the second one is the implications for texture of metamorphic rocks. So how does pressure affect the texture of metamorphic rocks? So for example, rocks that are subjected to high confining pressures, so if you imagine a rock that's been subjected to high confining pressures, they would typically be denser because they contain minerals that have a greater density due to their atoms being more closely packed. If you remember our example from earlier in this lecture, where the atoms were further apart, and then they become more closely packed. This is an example of how it becomes denser because of this high confining pressure. And because of plate tectonics, you can imagine that the pressures within the crust would not typically be applied equally. So you'll have regions where the compression is higher than others. So this can also be called directed pressure. We'll have a look at that in a bit more detail in the next slide. So unequal pressure in different directions results in directed stress, and this can be called deviatoric stress, which is our third agent of metamorphism. So stress can be resolved into three mutually perpendicular stress components. So we have sigma 1, which is the maximum principal stress, sigma 2, which is the intermediate principal stress, and sigma 3, which is the minimum principal stress. So if it was a hydrostatic situation, sigma 1, sigma 2, and sigma 3 would be equal. But with deviatoric stress, you will find that these would not be equal. So we have probably maybe sigma 1 would be bigger than sigma 2. We'll have a look at that in the next slide. So deviatoric stress affects the textures and structures of the rock, but not the equilibrium mineral assemblage. So it's purely on structure and texture, and this lateral squeezing component results in deformation. So this is what creates deformation in rocks. The examples on the side here, as we can see, so if we have larger stress in this direction, then that would result in tension. So we have gaseous opening. If we had compression, where we squeeze something together, you will get this squished rock in the middle. And if you had a shear, so if you imagine holding a deck of cards and sliding the top and bottom in opposite directions, that would create a shear. So with deviatoric stress, one of the most common results that you would get is foliation. And foliation allows us to estimate the orientation of sigma 1. What this means is that by looking at the orientation of minerals in a rock, you can try and deduce the directions of sigma 1. And there are three types of situations or examples that we can talk about where you can have foliation but no lineation. So foliation and lineation. So you can have a situation where you have foliation but no lineation. You can have a situation where there is lineation but no foliation. And a situation where you can have both foliation and lineation. So before we move forward, what is foliation? And what's lineation? Foliation and lineation are two terms that you will come across a lot when we talk about metamorphic rocks. So the first term, foliation, is a term that is used to describe minerals lined up in planes. And some minerals, especially from the mica group, are mostly thin and planar by default. So in foliated rocks, these minerals appear as if they are stacked, like pages of a book. And this is foliation. The word foliation uses the term folia, like a leaf. So imagine a leaf, imagine some books, those are planes. And in other minerals, such as hornblende, they're longer in one direction. So if you imagine pencils, needles, they're different to your planar shaped book. So with things that are long and linear like this, they can also be aligned within a rock, but that would be aligned as lineation. And our example here is a bunch of drinking straws tied together. So they're aligned, but they're not aligned in a plane. So if we do a cross section here in this plane, you will find that the minerals are aligned this way. But if you cut the rock in this plane, you will find the shorter, let me just change that color, you'll find the shorter axes of your mineral. And rocks can have both foliation and lineation, or just one or the other. So this top example here is a rock that has foliation and lineation. So what that means is that if you cut across it this way, you will see that they are aligned in the different planes. So we have that planar element, so it means it has foliation. And also you find that the minerals are aligned in the same direction. So in this case, these tourmaline crystals are aligned in the same direction on the foliation. So that it means that it has lineation as well. And our next example is foliation without lineation. So again, we get to make out the individual planes in the rock. So we have planes that displays the foliated plagioclase and hornblende, but on the surface you see that they don't have any alignment. So they're all over the place, but they're all over the place on the same plane. So this shows an example of foliation, but without lineation. Hope that helps. So if you just need to recall this really quick, foliation, think of pages of a book. So stacks of paper, but instead it's stacks of minerals. And for lineation, think about your good friends, the straws. And think about how tying straws together, they're aligned in the same direction. Okay, so I hope that helps. We'll move on to our next slide. Our last agent of metamorphism is fluids, and fluids enhance metamorphism by acting as a transport medium for mass transfer. It speeds up recrystallization and it speeds up chemical reactions. And by fluids, we're mostly talking about water, because water is the main fluid present within rocks of the crust. And the presence of water is especially important because this facilitates the transfer of ions, and when you have this transfer of ions between minerals and within minerals, it increases the rate at which metamorphic reactions take place. In other words, this speeds up the process. And water, especially hot water, can have elevated concentrations of dissolved elements, so ions get transported by hot water, and therefore it is an important moving medium. So it moves elements around within the Earth's crust, and this is particularly important in hydrothermal processes, as the name suggests. So it's hydrothermal, hot water. and in the formation of mineral deposits. We've taken a pretty deep dive into the introduction of metamorphism, so now we're going to take a step back and talk about why we would study metamorphism. So studying metamorphism ultimately is the interpretation of conditions and the evolution of metamorphic bodies, mountain belts, and ultimately the state and evolution of the Earth's crust. So you're taking one piece of information, stripping it back, and wondering how did it evolve into that state, and if it evolved from a previous state before that. So you're unraveling the history of rocks one by one, and you can do that by studying the rocks itself. And you can also go a step further and study the history and captured within minerals such as this zircon, which captures the history of its formation in the zones, the same way that you would study the history of a tree based on their tree rings. So metamorphic rocks retain enough inherited information from their protolith to allow us to interpret much of their pre-metamorphic history as well. So if you have a metamorphic rock, you can try and deduce what type of protolith it comes from and what conditions it may have undergone. So it's a lot of uncovering the history of rocks and ultimately the history of our Earth's crust. So it's less wibbly-wobbly, but more well-defined and informed deductions on the history of these metamorphic rocks. So that's why you would study metamorphism. And that concludes our very first lecture. It was a pretty long one, but it was necessary to set the foundation and to set the scene before our future lectures. If you have any questions at all, do feel free to get in touch and I will get back to you as soon as I can. I am currently based in Malaysia, so between us we will have an 8-hour time difference. So just keep that in mind if you're expecting an urgent response. Just remember that I am 8 hours ahead of you. Okay, so thank you again for your attention and hope to see you in the next lesson.